way. I like to have what I'm going to plot all by itself so Excel doesn't get confused with any extra headers or anything. So what I want you to do then for the lab is to go ahead and plot the temperature versus time, just to take a look at what it looks like. It's actually time versus temperature, I should say. Time on the y-axis. So it's kind of weird. This is one of those times when time goes on the y-axis. Usually time is on the x-axis. But here it's the independent variable. We actually do something about the temperature. We set the temperature. Not exactly, but we try to. So that's our independent variable. It goes on the x-axis. All right, so if I just select, Excel or Google Sheets, you can select the whole thing, or you can just select the upper left corner of your data as long as it's not too confusing. Excel and Google Sheets figures it out. I've had students ask me about this because sometimes I give, they have data that's 500 long. Well, then you have to click and drag all the way down to select the whole thing. You can also control and hit the arrows. There's little things. And I am recording, yes. So this is the easiest way to do it, though. You just click on the upper left-hand corner and say, give me a chart. And in Excel, remember, you need to always have a scatter plot. I'm going to get rid of the title because it's entirely meaningless to me. Just so that I can kind of look at the data and you can see that it looks like an exponential decay. I mean, I think it looks like an exponential decay. If you know what an exponential decay is, it looks like it. It decreases proportional to the amount that's in the that's the amount of y. Okay, so it's like compound interest in reverse, I guess. That's how the exponential term comes about. And in fact, in Excel, you can actually make this look a little bit fancier by adding a trend line and go ahead and you can make it exponential. And what that does, if you say exponential, don't worry about what the equation means because I don't care, but that makes a nice smooth line through it. All right, so just so that you can see it a little bit better, you can see that it's an exponential decay. That sometimes doesn't work, but that's specifically for this lab, it will work. Of course, in your report, you're going to put labels on these axes and things like that, but I'm going to leave those out just for the sake of time. I also want to see the catalyzed, okay? So what I can do is either double-click on the graph or right-click and do select data. I'm going to add another data set. You get this dialog box, which shows you what your original data set is already, and I can go ahead and edit that if I needed to. But I'm going to do add, and then it gives you a wizard here that you can give it a name. You can select a name from a cell, which is kind of nice too. So if I select that one, it becomes catalyzed so that it'll be labeled if I use a legend or something. If you hit these, I don't know if you know how these wizards work, but if you hit this part that looks like a little tiny spreadsheet, then it kind of collapses it so you can see your spreadsheet and grab what you need. So I need temperature on the x-axis, temperature on the x-axis, and then my y values are going to be the time, right? And well, I'm on like an extended monitor, and for some reason these dialog boxes get bigger. I don't know, but they do. Okay, so while I'm here, why don't I change the name of this? I'm just going to change the name to catalyzed, uncatalyzed rather, just for the fun of it, because that way I can show you when you use a legend what it looks like. Okay, so that's kind of nice. That's the difference between them. Let's add an exponential trend line there too, just so that we can see what's going on. And what you'll notice with your data and with this sort of fake data is this. They both have an exponential decay, but the blue one is changing faster than the orange one. If you want to add a legend, you can add a legend. Let's see, add legend. Let's put it on top. Ooh, that's kind of ugly. Let's move that. Let's put it on the right. Okay, there we go. Also kind of ugly. Change the font. All right. Now, something like that. I know that the orange one is catalyzed and the blue one is uncatalyzed, but maybe for your graph and the report, you could put a legend. And in fact, you can edit this legend. I don't know if you knew that, but I can get rid of the ones that, oops, are the fits, because those are kind of meaningless. So I just select those and say, get rid of them. So then it looks a little bit nicer. Okay. Anyway, little tricks and tips I like to throw in here. I want to move on and show you the analysis, right? That's the important part. Let's get rid of that legend since I don't need it right now, just to show you how to do this. We're going to need temperature in Kelvin. We're also going to need, I'm going to make this a little bit smaller. It's hard on this zoomed in screen to keep everything here. And then we'll need 1 over temperature, which is in inverse Kelvin, and we'll need the natural log of T in seconds. Let me make these columns a little bit smaller since they're just spacers. I use the spacers just so that when I want to plot these data, they don't get in the way, right? So I can do T is going to equal the temperature, and I did find out, let me just do this, 273.15, add that. I did find out that the best temperature to use is the one when the reaction occurs, right? So when you first start to see the blue color. So go ahead and use that. You may have timings that are more accurate than a second. Go ahead and use them, but I doubt that, we're that accurate anyway. We definitely have temperatures to the 10th because that's what the probe reports. So don't round off if you did get time in tenths of seconds or even hundreds, I guess, but that's an awfully quick time. So you can go ahead and put the whole thing in there. Just have to enter it once, right? I'm going to do just the first row so that I can grab and drag things down like I usually do. So this is going to be 1 divided by that temperature, and then natural log of the time goes in that cell. And then I'm going to go ahead and select all those, drag down and get all the data I need. And I'll do the same if I copy that and paste it down here. I have all my catalyzed data done as well. Okay. So now I can make a new plot with this data, which is the Arrhenius plot. Insert question? No? Okay. So I inserted a plot, and there's the data that I'm plotting. So I'm just covering up my data because I want to make sure it's nice and big. I'm going to add a trend line to this, which I want to be linear. I want to go ahead and display the equation and the r squared just so I have some idea of how well it fits. And you see it's really good. It does fit very well, and yours should fit pretty well. Maybe not quite as well as this, depending on which day and which data set, but yeah, you should get a pretty good fit. Okay, so there's the slope, 66.48. Of course, you should always use the slope function, which I will use in just a minute, but let's go ahead and take a look. Let's add the catalyzed data set to this, okay? So again, select data, add. This one is called catalyzed, and I'm going to select 1 over T, and then y, the natural log of T, and say OK. Say OK again, and then add a trend line for that. Display the equation, show the R value, get that out of the way. Let's move it so we can see it. There we go. Okay, so the slope is less, all right? If the slope is less, that means the activation energy is less, which is what we should get for a catalyzed reaction. And you will get that, although one of the days was not as good as the another one. I'll let you decide which one. Well, I mean, you won't know, but one of them was more obvious than the other. I'll tell you that much. All right, so what I want to do, I'm going to move this over here so it's in front of the data that I really don't care about, okay? I want to go ahead and calculate the activation energy now. So what I'm going to do is calculate the slope, okay, and use the slope function. So equals slope of natural log of t versus 1 over T temperature. Okay, so that now I have the slope, and the slope is going to be in units of K, right? Yes, because the x-axis is 1 over K. So the activation energy is equal to 8.314 times slope. I guess I don't need the parentheses there, but I did it already. That many joules per mole. So, like I said, it's pretty big. Let's make it kilojoules, so divide it by 1,000. You can do that all in one line, but oops, kilojoules per mole. Okay, so way too many decimals. Of course, in your report, you're going to report what you think should be appropriate number of decimals. Let's see, we know the temperature, typically 2 or 3 degrees, the time, or 2 or 3 significant figures, time and 2 or 3 significant figures, probably just 2 is appropriate. So just a whole number of kilojoules. And that's something that actually, if you do the error analysis, you find out that that's what it should be. The error ends up being about plus or minus on the order of a kilojoule, depending on which day again. So there we go, 55 kilojoules per mole for the uncatalyzed. How about the catalyzed? Well, I've already done those calculations, so I can just copy them down to here, right? And I get 46 kilojoules per mole, right, for the catalyzed. So there we go. We reduced the activation energy, and it made the rates go a little bit faster. Depending on the temperature, it has more effect at low temperature than it does at high temperature because of the Arrhenius relationship. But yeah, there you go. Can't think if there's anything else to add to that right now. I think that's pretty much it. So in the report, you would have maybe a couple of graphs that look kind of like this with the correct labels and everything. And then the activation energies. I think you should probably also report the slope, and the slope can be whole numbers as well. So, and then the slope is, or the slope times R gives you the activation energy. Okay, I think that's good. So I did mention that Sheets is a little bit different. Let's see, I think I have it just underneath this. Yes, okay, so I've done most of the calculations here, except for getting the activation energy, but I went ahead and did the 1 over T and the natural log, so that now I can plot those and I can show you how to do an overlay. All right, so for this one, I'm going to move that out of the way just so that whoops, just so that Google can figure out that this is my data. Insert chart. Okay, scatter plot is what I want. Temperature versus time, that's fine. So that looks good, right? Now I'm going to do it the way Excel, you would do it in Excel, right? The way you would add data, all right? So I'm just going to move this a little bit. I'm going to try to. Right now it's a little bit laggy, I guess. There we go. Now I can grab it and move it. So I want to add this data down here to this as a new data set. The problem is with Google Sheets, let's go back to that. Double click on that and I get the chart editor. Now if I go to the setup, I can add a data set, but all I can add is a series and I get the same x-axis. All right, so let me show you what that does. If I add a series and I want to add, I'm going to select a range, which is underneath here, unfortunately, but that should be right. Yes, yes, up to, well, no, those are the headings. There's 5 of them. There we go. Oop, I accidentally hit my right mouse. Yes, 19 through 23. Say okay. Ugh. All right, so it gives me garbage, right? And that's because, let me move this out of the way. Okay, actually, I should have changed that. Sorry, I'm gonna remove that and do it again. Add series, select a range. I should grab the header. Okay, that's a little bit better, right? Again, we can, let's see, select that data and do a trend line and make it exponential so that it kind of guides your eye. This one, trend line, exponential to guide your eye with the blue one, which is the uncatalyzed. But it's not the same. If you look carefully, the problem is I get the same X values for the orange, and the temperatures are not the same for the orange ones, right? I have different temperatures, so how can I get those temperatures different? And you may know this, I don't know how many people know this, but what you need to do is kind of combine the two data sets into one mega data set. Well, not mega, but a little bit larger data set. And trick Sheets into doing it correctly. So I'm going to go ahead and delete that. What you need to do is take your data from this data set that you want to add to the other one. Go ahead and copy it and then paste it underneath here. All right. But take this data set. So grab what you just copied for the Y values and move them over. Okay. And in fact, if you want to, you can change this to uncat and this one cat. I'm just going to do shorthand. Then plot this, and it'll plot the way it should be with an overlay. All right, so insert chart, and I want a scatter plot. It thinks I want a column chart for some reason. Go down to scatter. Now, select the data, and you'll see trend line exponential, orange, trend line exponential, and it actually gave me a nice legend as well when I did that, when I put the names up here. So there's uncatalyzed and catalyzed, and you notice that they have the correct X values now, the correct temperatures, and this looks exactly like the one in Excel. So let me do it again, just so that you see. I'm going to go ahead and delete that, and I'll show you how to do this data, all right? So you copy that second set of data, and then move this over. I need to get the hand, right? There we go. Move that over. You can make this uncat and cat. You should probably spell it out. I didn't. It looks like I erased it. I should probably leave it down there. Sorry about that. What did I do? I grabbed it and moved it? Oh, you know why? Because it's a calculated value, right? This is good. This is actually, when I did this yesterday, I maybe did the same thing. So these are calculated values. They're formulas. If I paste them up there, they're formulas, and they'll be, referencing something weird. They'll be referencing actually this temperature, for instance. So what I want to do instead is to select this, Control C, and then when I go up to here where I want to paste it, I'm going to right click and do paste values only, or you could do Control Shift V if you want. All right, so that copies the values. The other thing you could do is to reference the values below, which maybe is a more elegant way of doing it. So let me do that. I'll say equals that value. And then I can drag this over, and that equals that value. Drag that down, and now I have all those referencing the one down below. Now I can take this and move it over. The reason that's more elegant is because now if I change something over here, that wasn't 20 seconds, it was 25, then everything updates, all right? If I paste values, then those are like I typed them in. They're hard-coded, if you want. Okay, now we're on good. This is uncount. Okay, now I can do the graph. So you select the data, and then do insert chart. And this time, for some reason, it knew that I wanted a scatter plot. Maybe because I already did it? I don't know why. Yeah, that's bizarre. Oh, maybe because that one was next to it? I don't know. Anyway, select the data, do a trend line. I want to have it linear, and I want the label to be the equation, and I want to show the r squared. Okay, so the label actually goes up here in Google Sheets. And do the same for the catalyzed trend line, linear, use equation, show r squared. All right, so that's a pretty nice graph of the Arrhenius drawing. You notice that the x values are in the right places. Those are the slopes, and those should be the same slopes as I got for Excel. 6648 and 5554. Let's see. 6648 and 5554. So you get the exact same answer. Everything else is the same in Sheets. You can use the slope function, multiply by 8.314, set the, divide by 1,000 to get kilojoules, and you're all set.